Morning, everybody. So welcome to the plenary lectures from the IAUS369. It's my great pleasure to be able to introduce two speakers this morning who are going to bring to a new audience and the wider astronomical community the most recent results on the exciting, useful, and mysterious sources called fast radio bursts. There'll be two speakers this morning. The first of the speakers will be Professor Victoria Kaspi. She's a professor at McGill University, where she holds the Laurent Trottier Chair in Astrophysics and Cosmology and the Distinguished James McGill Chair. She's the inaugural director of the McGill Space Institute, and I've been fortunate to have known Professor Kaspi for all of my academic career, and her work using radio and X-ray astronomy to study both pulsars and magnetars have led the field in many ways and led to many great advances. And she was very, well, I hope she was fortunate to win the, in 2021, she was co-awarded the Shaw Prize in Astronomy for her work on magnetars. She is also a fellow of the Royal Society of London and an elected member of the US National Academy of Sciences and the American Academy of Arts and Sciences. And in 2017, she was named Companion of the Order of Canada. And since 2014, she's been working on fast radio bursts, the topic of her plenary talk today. And she's presently the principal investigator of the CHIME FRB project. Professor Kaspi, would you?
Hey, thank you. Can you hear me? Okay, great. I'm here to tell you about the astrophysical mystery of fast radio bursts. It's a puzzle, and if you have been attending the IAU Symposium 369, you've understood that we don't really know what fast radio bursts are. It's quite an interesting astrophysical mystery. But one thing I can promise is that by the end of this talk, you too will not know what fast radio bursts are, but you'll at least know what you don't know. The story of fast radio bursts starts with one event that we know as the Lorimer burst, which is depicted here. The plot here, oh, you can't. My laser is too dim, but on the x-axis of this plot of radio data obtained at the Parkes Observatory, which is shown in the picture, which is located in Australia. The x-axis on this diagram is time, and it's a total of half a second, 500 milliseconds, whereas the y-axis is radio frequency, going from about 1.4 to or 1.2 to 1.5 gigahertz, which was the available bandwidth for the receiver at Parkes. And the horizontal line you can see there, about 1.34 gigahertz. That's a terrestrial interference due to a television station. Uninteresting. The astrophysical signal that we're interested in is the line that's sweeping through the band, arriving earlier at high frequency and later at low frequency. And if you have good eyes, you'll see that that sweep, that dispersion of the radio waves is not linear. It actually is a little bit parabolic. And it's a familiar phenomenon, cold plasma dispersion, where the time delay between two different radio frequencies goes as 1 over frequency squared, with a constant of proportionality that we call the dispersion measure, which is this cold plasma dispersion is observed ubiquitously in the galaxy for radio pulsars as always something that one has to correct for. And the physical origin is that free electrons are radio waves are dispersed by free electrons. And the total amount of dispersion is proportional to the integrated column depth of free electrons. And so this dispersion measure is basically the integral of the free electron density along the line of sight. Now, so an object that is particularly close will just be vertical in this plot. All the radio waves will arrive at the same time. The further something away is, the greater the dispersive sweep. And we have known how to quantify the distance to galactic radio sources for quite a while because we have radio pulsars with independent distance estimates. And that's what this is. This is a model of the Milky Way galaxy. It's actually a three-dimensional model, but shown here is just a slice through that three-dimensional model in the galactic plane, as if you were looking down on the Milky Way. The plus sign near the center there, that's the center of the galaxy, and the Pac-Man near the top, that's the solar neighborhood. And you can see schematic spiral arms. And what you see are contours of constant dispersion measure. So that for a galactic source, if you just detect it in some direction, and you can measure its dispersion measure directly, you can know roughly how far away it is in our galaxy. Now, for this model, in any direction, there's a maximum dispersion measure. That is, the galaxy eventually runs out of free electrons. And so for any direction in the Milky Way, there's some maximum dispersion measure that is predicted by this model. And the model is fairly well calibrated, as I said, by pulsars with independent distance estimates, such as pulsars in supernova remnants, or pulsars with binary companions, or pulsars with measured parallaxes. And so coming back to the Lorimer burst, the dispersion measure here in the dispersion measure units was quite large, especially when considering that in the direction that it was seen, the maximum, according to our excellent, our pretty good, well, I shouldn't say excellent, but pretty good models for the distribution of free electrons, was just 25. So this is enormous, much larger than you expect from the Milky Way. And that right away had the discoverers quite excited, because naively, it would imply a cosmological distance. We expect that the plasma in the intergalactic medium is extremely tenuous, and so to amass so much in that integral, the dispersion measure, would require you go out a very far distance. And for a cosmological distance, that would imply tremendous luminosity. This would have to be something extremely bright, far brighter, orders of magnitude brighter than any short radio transient that's been seen before. And I should say that when we have data like this, we can de-disperse it. We measure that slope, the dispersion measure, and that's what the inset is. The inset is taking the same data and in software correcting for that 1/frequency squared law, and then summing up over the entire bandwidth. And in this case, you see a very narrow pulse, just a few milliseconds. And a few milliseconds, but with a tremendous implied luminosity if this argument for the dispersion measure is correct. So, really a cosmological distance? Well, here's the argument. Models, and up until recently, we've only had models for the amount of the free electron density in the intergalactic medium. Models based on the baryon density and assuming it's all ionized. The dispersion measure in the intergalactic medium has been modeled to be approximately 1,200 times the redshift, which for the Lorimer burst would imply a redshift of 0.3. So indeed quite far, about a gigaparsec away. But this is likely an upper limit, because although there's this, all we measure is one number, the total dispersion measure, and that consists of multiple components. There's the component due to the Milky Way galaxy, the component due presumably to the Milky Way galaxies are thought to have halos. And both of those numbers, we have rough estimates for those, one from the model I showed you and one from estimates of what the halo should have. There's the intergalactic medium, of course, and then probably this event originated in some host galaxy, which itself has an interstellar medium and contributes some dispersion measure. And we don't know what that number is. So let's say you just split the difference After subtracting from the Lorimer burst the Milky Way component, an estimate for the halo, you split the difference between the intergalactic medium and the host galaxy. That's still pretty large, for let's say 500 megaparsecs. And that sets the energy scale to be about 10 to the 40 ergs for the Lorimer burst, or in terms of luminosity, 10 to the 43 ergs per second. Many orders of magnitude greater than anything that's been seen in terms of a short radio transient in our own galaxy. Since 2017, so as of 2017, roughly 24 fast radio bursts had been observed, all very short, few milliseconds long. And from those 24, which were detected using mostly Parkes, and I'll show you other telescopes that did some of these detections, typically with very small fields of view on the sky, and not observing 24 hours. So if you correct for, you take into account the fraction of the sky, which was tiny that they could see, and the amount of time they were on sky able to detect these short dispersed radio bursts, they could infer that in spite of only seeing 24, the all sky rates of fast radio bursts had to be enormous. This is not an anomaly. This is not something rare. Something like 1,000 per sky per day. This is, and consistent, at least for those 24, with being approximately isotropically distributed on the sky after correcting for some effects. Most of them, like the one shown in this diagram here, are single-peaked, and some even had the telltale scattering broadening that you see in this diagram, that we see ubiquitously for radio pulsars in our own galaxy, where you see that there's a tail, what we call a scattering tail, and that's due to inhomogeneities in the electron density along the line of sight. So if you had some emitted pulse that is a single narrow burst, that would go in many directions. If it encounters some inhomogeneities, perhaps due to turbulence in the plasma, that could redirect radio waves back toward the observer, but with a time delay, and that's why you see that highly frequency-dependent tail. So some fast radio bursts show this. Some have multiple components. We sometimes see multiple components. I'll show you examples of those, and some repeat. So sometimes, the Lorimer burst, it went off once and disappeared, was never seen again. But some fast radio bursts, as I'll show you, you'll see multiple bursts if you're patient enough and you look at that same part of the sky, all at the same dispersion measure. And the inferred energy range of the detected sources as of 2017 was about 10 to the 35 to 10 to the 43 ergs, quite a large range of energies. For recent reviews, I point you to these references. Now you might say, okay, so what did it come from? Why don't you just look with an optical telescope and see if there's a galaxy there, and you can then know something about the fast radio burst. If you could identify a host galaxy, it would determine the redshift directly. You could set the energy scale without any assumptions, and you could see what type of galaxy it was. Is it a young galaxy, an old galaxy? That would give you some hint to what this burst came from. Now, the problem is that there are many galaxies in a typical single-dish radio telescope error region. So for the Parkes radio telescope, size of the region is many arc minutes. And there's hundreds of galaxies in that area. So you can't know. Now, you can increase the aperture of the telescope and say, let's say you went to a much larger aperture, the now decommissioned Arecibo telescope. That would help, but it still wouldn't solve the problem. What you really need in this game is to have a very small field of view, as is available from an interferometer. Not a small field of view, good, very small error region, excellent angular resolution. But the problem then is that interferometers typically have very small fields of view, and if you want to detect an object, not knowing where or when it's going to arrive, you're not going to detect many that way. So this is a problem. On the other hand, as I said, some fast radio bursts repeat. And this is the first one that was detected, that was seen to repeat, discovered with, as I said, the Arecibo Observatory, then functioning in Puerto Rico. And this was an event that was seen to repeat after many months of staring, where we didn't see anything. Suddenly, there were 10 bursts in an hour. That was very shocking to us, and immediately ruled out cataclysmic models for at least this source. So if you might think, oh, you could have a tremendous radio burst from merging neutron stars. Well, they can't merge 10 times an hour after many months. And what was interesting is we immediately saw they could have a variety of morphologies. You can see some have multiple peaks. And they also had a variety of spectra and variety of fluxes. Some bursts from the source. And these, in this case, I should say, they've all been de-dispersed. So that dispersion sweep has been removed in software, so they're vertical lines. And they're all at the same dispersion measure. So we know it's the same source, same position on the sky, same dispersion measure. And you can see the spectra change radically. So you have bright bursts, some very bright in the lower part of the band, some bright in the upper part of the band. And the bursts tend to cluster in this source. They're not Poissonian. That's a clue. Now, in addition to telling us clues about what the object is, it enables localization, because now you know where to look and hope to see a burst. But first, I'll just mention that since that discovery, the FAST telescope, tremendous sensitivity, excellent for following up these objects, has now detected thousands of bursts from this event. It's an interesting energy distribution. It's bimodal. We're not sure why. You might wonder, is there a periodicity observed? No periodicity observed in this one, but I'll come back to that point. In any case, with a repeating source, you can go to an interferometer and patiently wait, and it took many hours of detecting nothing until we finally saw this source. And then once you have the position, and it was detected with the very large array, that at the right dispersion measure, here shown in the error region defined by the Arecibo Observatory, that little square, you can then go to an optical telescope. You see how this works, and you beg for time at the optical telescope, and they let you look. And for the first event, it was for the first repeater that was localized, it was quite a surprise that it was localized. There's the Gemini image in blue at the bottom to a tiny dwarf galaxy. And that was quite puzzling. That is quite puzzling. Why is it a dwarf galaxy? Should we have expected that? But the good news was that you can measure the redshift. Indeed, it was at a cosmological distance, so that argument from the dispersion measure holds. Subsequent localizations using the European VLBI network and the US VLBA provided a sub-arc second position, tens of milliarc seconds, which then could be used with the Hubble Space Telescope to show the object was in a knot of star formation within that dwarf galaxy, which is a major clue. It says, these are young objects, or at least this object is young. That was interesting. Now, so fast radio burst repetition, what does that tell us? Some repeat. There are some that have not been seen to repeat. Does that just mean we haven't waited long enough? Do they all repeat eventually? We don't know. There could be two classes, repeaters, non-repeaters, but we don't know. So perhaps some are cataclysmic and others are not. But for the repeater, what could it be? These short repeated bursts, they're definitely reminiscent of, for example, giant pulses that have been long studied from the Crab pulsar in our own galaxy. But they're at a totally different energy scale. The Crab pulsar is the maximum, its rotation power, the rate of loss of rotational kinetic energy due to magnetic braking in the Crab pulsar, it sets the maximum allowable luminosity of 10 to the 38 ergs per second, orders of magnitude less than what's inferred for this and other FRB, for the, say, the Lorimer burst, but for other FRBs and for the repeater. Another possibility is magnetar giant flares. Magnetars are ultra highly magnetized neutron stars, extremely volatile, that tend to have massive explosions in X-rays and gamma rays, very well studied. Certainly enough energy available there to produce something like the repeater that I've been describing. But on the other hand, the typical rate of giant flares for magnetars, at least for those in the galaxy, is something like 1 per decade, hardly 10 per hour. Also, the energy scales are quite different, as I'll describe soon. So phenomenology is not, and energetics are not exactly right, but it's still a promising idea. Since then, the Australia telescope SK Pathfinder has been finding fast radio bursts and able to localize them immediately because of the multiple telescopes at large baselines. And here's a montage of 6 more fast radio bursts, not repeaters, that have been localized. In those cases, and in subsequently, and we've heard at the symposium, there's lots more been localized. 24 have been localized by ASCAP, and most are in massive galaxies. So the fact the first one was in a dwarf galaxy might have been a bit of a red herring. We're still trying to understand that. But you can see, for example, there's one in a spiral arm. The bottom line is that they're being found in a variety of different types of galaxies. So there's not yet a clear picture emerging on that front. On the other hand, oh, and I should mention that I've also learned at this wonderful meeting that Meerkat telescope is also producing wonderful results, very exciting. So although the picture about the host galaxies is not yet clear, one thing that is enabled by localizations within galaxies, and you're going to hear a lot more about this in the subsequent talk, is studying cosmology and large-scale structure. So you can plot the dispersion measure excess, that is the amount that you think is contributed by the IGM, and of course there's some unknown host component there, as a function of now measured redshift because you've identified the host. In this graph, you can see there's 5 solid localizations that were used in this sample. The black line there is the prediction based on Planck cosmology of the baryon density. And those baryons have long been, it's been a long-standing problem, this missing baryon problem. Where are they? Presumably they're in the intergalactic medium, but hard to detect. Now we have a way to detect them, and we can check. The gray region is the expected scatter due to the cosmic web. So this perhaps, and the fact that the dots all fall very close to that relation, suggests perhaps the missing baryons have been identified. It was just a sample of 5. Those early times, you'll hear more in the next talk. But it's very exciting, and it shows the potential for using fast radio bursts as novel probes of large-scale structure and cosmology. In any case, another thing this highlights is you'd really like to have more fast radio bursts, both to answer questions like, do they all repeat? You want lots of fast radio bursts where you can monitor them regularly. And you'd like to know, are they truly distributed isotropically on the sky? What sort of luminosity function do they have? And what sort of morphology distributions do they have? Spectral distributions. You'd like to really solve this problem with a large number of fast radio bursts. And so that is what the CHIME telescope has been providing. This is the Canadian Hydrogen Intensity Mapping Experiment, located in Canada, in British Columbia. Hydrogen intensity doesn't sound like fast radio bursts, and that's because the telescope was originally designed for hydrogen intensity mapping to study the baryon acoustic oscillations, so for cosmological purposes, but it turns out it's a fantastic fast radio burst detector as well. It's not a traditional radio telescope, it's a cylindrical, consists of 4 cylinders that are 100 meters by 20 meters. The total collecting area in standard Canadian units is about 5 hockey arenas. Along the axis of each cylinder are 256 antennas, each sensitive in the frequency range of 400 to 800 megahertz. They're dual polarization, so we have a total of 2,000 inputs, all going into a magnificent, large, and extremely powerful correlator that digitally produces 1,000 beams at once within the large primary beam of the cylinder. The primary beam in the north, so the cylinders are oriented exactly north-south. And there's no moving parts here. This is a transit telescope that's always staring above as the sky rotates. So it's exactly north-south. The north-south field of view is 120 degrees, and the east-west field of view is a few degrees. So we have a total of over 220 square degrees, orders of magnitude more field of view than conventional single-dish radio telescopes, which is what makes this so excellent for studying transients. The digitally formed beam sizes I'll show you is much smaller, and when you have, and this is a collaboration of many different institutions, and a whole bunch of them are here in the audience, so you can, chances are you're gonna, if you're curious about this, you talk to your neighbor, and they might be from Chime. The way this works is that if you have one antenna on a cylinder, it focuses in the east-west direction only, and the north-south direction is just a mirror. But if you add many cylinders on the axis, you can do FFT beamforming and produce multiple digital beams in the north-south direction, and then you can populate all of the antennas with all of the cylinders with antennas, and also get east-west spatial resolution. So we have effectively, and this is the real diagram of the Chime beams, 1,024 digitally formed beams. They have interesting morphologies, interesting chromaticity. But the bottom line is that the Chime telescope is like having 1,000 green bank telescopes all operating simultaneously and producing data, 1,000 different data streams, different positions on the sky that we can search for fast radio bursts. This is done using a trigger system. So the input data rate is 6.5 terabits per second, which gets channelized so that we can do search and dispersion measure, and sampled at 1 millisecond at a total data rate of 142 gigabits a second. And we're buffering data in each of those beams so that when our software pipelines detect an FRB, we quickly save that data. But if we miss it, it's gone. We can also save raw voltage data and later recover higher time resolution data and polarization information. All of the computing is located in these shipping containers directly, RFI screened shipping containers that are located directly adjacent to the structure. We started detecting fast radio bursts in 2018, and here you can see, this was exciting, the first fast radio bursts that were seen by ASCAP and by Parkes were at 1.4 gigahertz. Here we're at a lower frequency, so it's quite exciting to see fast radio bursts down to 400 megahertz. Since that time, LOFAR telescope has beat that record and is now seeing fast radio bursts down to 110 megahertz. Very exciting. This was the number of fast radio bursts detected by a variety of different facilities prior to Chime turning on. You can see ASCAP was, and continues to find many of them. With Chime, it's a new ballgame because we can find, our detection rate is on the order of 3 per day. And so we found many hundreds of fast radio bursts, and we've been able then to produce a catalog. So our first catalog contains over 500 events. And with a large sample like that, we can now do things like test, is it consistent with isotropy? Indeed it is on the sky. We can measure the fluence distribution, and we can see if you model it with a power law, it is consistent, we find, with the standard 3 halves in the log n log s distribution that you expect for a non-evolving population in a Euclidean space. And you might say, wait, you said they're cosmological, but the Chime sample, the peaks at around redshift of 0.5, so we are starting to detect effects of cosmology, but in this initial catalog, we don't see that. Here you can see some of the distributions in dispersion measure space. We've also very carefully measured using a system of injection of fake fast radio bursts to quantify very carefully our selection biases. To see, you can see at the top there, that's our selection biases against different dispersion measures, actually very modest. Our top dispersion measure we see is out to 3,000, and that's not because we're not sensitive to them. It's probably because they're too faint, they become too faint at that distance. On the other hand, we're highly biased against finding fast radio bursts that are highly scattered. You can see here the selection bias is very great, above 10 milliseconds of scattering in our band. So we know that we're missing a large population that might be much more observable at higher radio frequencies by other instruments. And the degree of scattering, quite interesting, is much higher than you would expect for interstellar medium like we have in the Milky Way galaxy. That's actually quite interesting. It suggests that these objects are in a very unusual, or on average are in unusual locations. We also now release in near real time every event. We sent out an alert via the VO events system, and we have lots of subscribers. And I encourage anybody here, if you're interested in following up fast radio bursts, the latency is very low, and we have nice video tutorials on how you can get your CHIME FRB alerts and do whatever science you like to do with them. CHIME maps the entire sky every single day, so we're also very good at finding repeating sources. And we've published now 20 new repeaters, opening up a new population for lots of people to do follow-up on. Repeaters tend to have very complex morphologies. That's quite interesting. They're often seen to be band limited. You can see the central one there is an excellent example of that. Band limited, but sometimes with drifting bursts that drift downward in frequency. We call that the sad trombone effect, because it sounds, imagine if it would sound a little bit like a sad trombone, you know, like wah, wah, wah. So that's what it looks like. It goes down in frequency, and that's seen very, very commonly. So there's morphological distances. The repeaters tend to have broader pulses and narrower bandwidths. On the other hand, so that suggests that's quite interesting, whereas apparent non-repeating FRBs tend to be extremely broadband and less often have multi-components. On the other hand, the dispersion measure distribution of repeaters and the scattering distributions of repeaters, we currently in our sample don't see a huge difference between those and the non-repeaters. So you might think if they're two different classes, perhaps they should have, maybe they're distributed in the universe differently. They should have different DM distributions or different host galaxy, maybe they have different environments. Currently, we don't see any evidence for that, so that's sort of a puzzle. And we heard a talk from Ziggy Planis that we're preparing another 40 or so to release soon. And here's a diagram where you can see this is a measure of how broadband it is on the y-axis and the measure of an intrinsic width. And you can see the repeaters are in orange and the one-off bursts are in green, and they clearly inhabit different regions of phase space. One of our repeaters shocked us in that it's periodic. So one of the repeaters that is particularly likes to go off a lot always goes off every 16 days in a 4-day activity window. You can see here the exposure. We have lots of exposure. We look on the sky every day with CHIME, but you can see the little red arrows are where we see bursts, and this cycle has persisted. We don't know the origin of that periodicity. You can speculate. But that enabled the source to be localized, again, by the European VLBI network. And that enabled Hubble Space Telescope observations that could pinpoint the location of the fast radio burst to just outside a star formation region, which suggests youth, but not something that's not too young. That's kind of puzzling. Could it be a magnetar? But we said magnetars don't really explode 10 times in an hour, or many don't have that. It would have to be very young, active magnetar, perhaps, but then why isn't it inside the star formation region? That's a puzzle. And we've heard talks about this source as well. There's another, I'll mention very quickly, another potentially repeating fast radio burst. The original repeater I showed you from Arecibo, it seems to have 157-day periodicity. Perhaps if you wait long enough, you'll see periodicities in all repeaters. We don't know. And what could be causing that periodicity? Could it be a binary or precession? We've heard talks about that. I don't think we know. The jury's still out on this. Speaking of periodicities, we've recently discovered a very short timescale periodicity. The other two were much longer, 16 days, 157 days. Here, we see in one burst that has not been seen again. So this burster doesn't seem to be a repeater, except for the fact that it showed 9 bursts within 3 seconds, each separated by 212 milliseconds. And pretty strictly separated, so the periodicity is quite significant. 212 milliseconds, that sure seems like a neutron star, doesn't it? We also, in 2020, detected a luminous radio burst from a galactic magnetar, a known galactic magnetar. Magnetars had been shown to have radio waves before, but nothing anywhere near this luminosity. This was also detected by the STARE-2 telescope operated by Caltech. And you can see here the dispersion measure in this case was solidly inside the galaxy, as you'd expect for a galactic source. And then in the far diagram, you can see this is now a diagram with distance on the x-axis and the observed fluence on the y-axis, where the nearby galactic radio pulsars are shown in the bottom left corner in blue dots. And you can see there's the Crab pulsar. This source is now at the very top of that diagram. So it's still in the galaxy at a close distance, but it has an enormous luminosity, many orders of magnitude greater than anything we've seen from the galaxy before. This is very exciting. This is a fast radio burst inside our own galaxy. If you put this in a nearby distant galaxy, it would look just like a fast radio burst source. Now, on the other hand, the FRBs that we know of, they're at much greater distances, as inferred either from host galaxies or from host galaxies with redshifts or from the dispersion measure. That's why some are quite uncertain. But you see they're typically of the same fluences as galactic radio sources, but at much greater distances. Then the diagonal lines here are lines of constant energy. So what you can see is that, and if you can't see the labels, the energies of the fast radio bursts, of course, are much, much larger, dozen orders of magnitude greater than galactic radio pulsars. But this one burst from this galactic magnetar bridges a huge gap. That if you follow the line down, or the diagonal line, it is of the same energy as the least energetic fast radio bursts. So it suggests some FRBs could be magnetars, but does it prove all FRBs are magnetars? No. We have many orders of magnitude yet to bridge. These are lines at every factor of 1,000. So you see it's 1 million to 1 billion times less energetic than some FRBs we've seen. Can a magnetar do that? We don't know. And by the way, this is among the top 10 science results of 2020 in both Nature and Science magazines. But the leading result was the COVID-19 vaccine. And to that I say, fair enough. A last result I'll just mention is a very recent result where we found a fast radio burst in the outskirts of the M81 galaxy, very nearby, only 3.6 megaparsecs. In the H1 disk, not in the optical disk. Something this close makes a wonderful opportunity to try and look for multi-wavelength counterparts. We've yet to see a counterpart to a fast radio burst at any other wavelength. X-rays, if it's a magnetar, you might expect to see X-ray bursts. Something people are looking for. But very curiously, and just to end with something very puzzling, this source, again localized with the EVN, is in an M81 globular cluster. And there we scratch our heads again, because globular clusters are not known to have very young objects. So if you think these things are magnetars, which there's lots of evidence, a globular cluster is not an expected venue for a very young object. Maybe there's some mechanism that old stars could form magnetars, some sort of merger, maybe? We don't know. So that's another puzzle. And I'll just say there's lots of instruments coming online that are going to help solve this problem. So I've left you with a puzzle. I hope I've whetted your interest, and you'll come to the last day of the Symposium 369 to hear more about these strange objects. But we're building outriggers to the CHIME FRB system, so that outriggers across North America, so that we can pinpoint them and localize to within 50 milliarc seconds every CHIME FRB. DSA 110 is being built in Owens Valley by Caltech, and is taught by Liam Connor. We heard about, they'll have 1 arc-second localizations for 100 FRBs per year. The Krakow upgrade to the ASCAP telescope will get 1 arc-second localizations for 300 FRBs per year. so on and so forth. Lots of exciting science to come. And so, yeah, you can see the outriggers for CHIME are actually already being built, one in British Columbia, one in Green Bank. And a summary, we still don't know what they are. Maybe there's multiple classes, there's a variety of hosts and environments, but it's still early days and there's many instruments coming online that are going to help solve this. But regardless of what they are, they have great potential as novel probes of large-scale structure and cosmology, which is the subject of the next talk. And thank you for your attention.
Thanks very much, Vicky, for this fantastic tour of fast radio bursts. The floor is now open for questions. If people have questions in the audience, we have time. Yep, go ahead.
Mike?
How many FRBs has CHIME discovered?
How many FRBs has CHIME seen? Right now it's over 3,000.
Okay.
We're working on second catalog.
We'll go left and then in the middle again.
That was great, thanks. So what can you learn from the scattering distribution? Is that telling you the difference between like the local environment, the electrons in the local environment versus the intergalactic medium?
Yeah, so we think that the scattering in the intergalactic medium is probably not very large. In fact, we think that's probably a tiny component. But in circumgalactic media of galaxies, there has been proposed potentially to be scattering possible, but it's quite unknown. So you could have scattering either in the interstellar medium of the host, or perhaps in the local environment, the very nearby environment. Let's say it's in some dense supernova remnant or something. So there's multiple regions where you could have scattering, and it's something that we can disentangle as we detect more of these, more scattering tails. We can look for how many galaxies, say, are along the line of sight. We heard a talk like this in the symposium, and you can see, okay, can you correlate with the amount of scattering, let's say the number of galaxy halos that you intersect. If there's scattering in the halos, you might expect more. So it's one way to probe that, or perhaps you'll see that that it's not correlated, in which case that would implicate the local environment more. Curiously, we don't see a very strong correlation between scattering and dispersion measure. That's quite interesting. Or scattering and rotation measure. I didn't have time to talk about that. But there's all sorts of things you can do. You're left with this imprint on the radio waves, on the burst. That's very informative. That's why they make such great probes.
Yes, hello. Thank you. It was very interesting. So could you give us a flavor of how magnetars could produce such bursts? Why in radio and not in other bands like invisible, X-ray, gamma, whatever?
Yeah, no, that's an excellent question. So the classes of models that involve magnetars are of two flavors. One where you have some sort of event, and in that case, that then interacts with a circumstellar medium to produce a synchrotron maser emission. And in that case, you expect short bursts of radio waves, but you also expect other wavelengths as well. And X-rays is one that's, as you suggest, would be very good to look for. But you can predict the sorts of radio to X-ray efficiencies, and you do expect to see X-rays, but really current technology would only allow you to detect them in the nearest sources. The other class of models involving magnetars are where it's not a sudden emission of energy slamming into a circumstellar medium that then produces maser emission. It's directly in the magnetosphere of the magnetar, presumably due to some catastrophic instability in the magnetic field along the line of reasoning that has been invoked to explain giant flares that are directly observed in our own galaxy from magnetars. It would just have to be, much larger. And there's problems with that in terms of optical depth, but that's one of the active areas that people are trying to understand.
Okay, very quickly, there's a question from online from Siu-Won Chang. Thank you for the great review. Please give a brief comment on what is the right path of multi-messenger efforts, somewhat related to the question we just had. What kinds of further potential information can be gleaned from multi-wavelength, especially optical bands and multi-messenger detections of FRBs in the near future? And you have approximately 1 minute to summarize all of that.
Yeah, well, I think there's lots of opportunity. We will hear a talk today about potential coincidences between fast radio bursts and gamma ray bursts, for example. None has been seen just yet. Or there's a paper that's on the archive searching for coincidences between LIGO events and fast radio bursts, and we had a talk on a possible candidate for coincidence in the symposium. So there's all sorts of opportunities. It's a very exciting field, and I'd say stay tuned or get involved. Like we can use more people to solve this problem.
Absolutely. Okay, with that great advertisement for people to come and join the field, let's thank Professor Kaspi again. Okay, so it's my pleasure to introduce the second plenary speaker in this session. So Professor Xavier Prochaska. He's the Distinguished Professor of Astronomy and Astrophysics at the University of California, Santa Cruz. He is also an affiliate of the Kavli Institute for the Physics and Mathematics of the Universe. His scientific career has focused on the observational analysis of gas in and around and in between galaxies, primarily in the distant universe, typically referred to as the interstellar medium, circumgalactic medium, and intergalactic medium. Observationally, he takes spectroscopy of static and transient sources, quasars, gamma ray bursts, and of course now fast radio bursts, and the fields around them to probe the universe. And so today he's going to tell us about how we can use fast radio bursts for some of these exciting studies. Please take it away. Yeah.
Thank you. And good morning, FRB enthusiasts. Nice to see you all here today and presumably around the world. I'm here today on behalf of a team, which I would like to introduce to you. We call ourselves the Fast and Fortunate FRB Follow-Up Team, or F to the 4 in short. As you can see, it's a pretty modest-sized team of primarily young researchers, including myself and some senior folks around the planet. A few more here in the next slide. But I'm also here on behalf of the FRB community, which has been holding our annual symposium here at the IAU down in room 101. You're encouraged to follow me there after this talk. It's a wonderful community. Many of us are here in the audience, really expanding the entire world. Most of the large or even small radio telescopes in existence on the planet are either searching for FRBs or following them up in some fashion. In fact, if you've got a backyard and some chicken wire and a couple of spare GPUs, find Keith Bannister. He'll help hook you up and get you involved in the game by the end of the day. So we've been, this week, highlighting some of the new advances in the field. I've been tasked with describing how we are using fast radio bursts to probe the universe. And let me jump into that now. Vicky, in her wonderful introductory plenary on the topic of fast radio bursts, gave you a sense of the wild and wacky and unknown aspects of FRBs. There's an entire science thrust in trying to understand what makes them tick, what makes them burp, what makes them repeat. I'm going to describe another thread of research, which is using them as probes of the universe, which in itself is a pretty broad effort, which is also what really excited me about using FRBs for my own science. So there's a breadth of activities. I've organized the talk into kind of 3 areas. The first will be kind of from smaller scales to the more grandiose scales. On the smaller scales, these events do occur within galaxies. We call them host galaxies. Here's one image with the Hubble Space Telescope. The red dotted circle is an approximate estimate of the localization of the FRB. You can see it occurred coincident with a spiral arm, coincident with a star-forming region within that spiral arm. And FRBs offers the opportunity to study in a unique way, in a number of unique ways, the interstellar medium of these, I would say, normal galaxies that we've been associating them to. For a handful of events, more rarely, the signal will intersect an intervening galaxy. The galactic halo of that galaxy, we often refer to that as the circumgalactic medium. And the gas and magnetic field within that halo of that intervening galaxy can impose its own signature on the signal, and that allows us to probe it directly. And then on the largest scales, we have the opportunity to study the gas throughout our universe, so-called cosmic web, and I will describe some of the efforts there as well. Let me begin, though, by quickly re-reviewing the range of signals that are present in the FRBs. Vicky went through most of these in hers, so I'll just pass through them rather quickly. But it's this multitude of signals that give us multiple threads of science and scientific measurements on gas on scales of the interstellar medium to the intergalactic medium. The first and foremost is the dispersion measure. It's really what defines a fast radio burst. It's how they're detected. We trigger off this sweep of frequency and time. As Vicky introduced, that delay in the lower frequency radiation that arrives to the radio telescope goes like frequency to the -2 power. And it's also proportional to the amount of material that the signal intersects. That's what we refer to as the dispersion measure. It's a sightline integration of the electron densities weighted by the scale factor if you get out to cosmological distances. And it's this DM which really gives us the probe of electrons on scales from the very local universe to as far as the FRB itself exists. Another aspect of the signal is its localization, its position on the sky. I'm going to focus on events that have been precisely localized. As Vicky mentioned, the first one of these, known as R1 or as the repeater, was localized because it repeats, and folks were able to point an interferometer at this poorly localized repeating source, or somewhat poorly localized, and then very precisely localize it to subarc second precision and to the galaxy that's pictured in the blue image. Today, interferometers are detecting them directly, and then a few days later, in the analysis of the dumped broadband, the baseband data can localize to subarc second precision, and the key point being then associate them with an individual galaxy. If the signal propagates through a magnetized medium and is polarized, then the angle of polarization will be a function of the frequency. That's known as the rotation measure. Here's an example of that angle varying with frequency for one of the FRBs detected by the ASCAP telescope. And that rotation measure is an integral property of the electron density, again, along the path line, but here weighted by the magnetic field oriented along the sight line. And so one has a measure of the magnetic field within the medium between us and the fast radio burst event. There's the light curve, or what transient folks might call the light curve of the FRB. Its emission is a function of time, typically only a millisecond, of order of a millisecond or less. This is a less exotic-looking light curve. Vicky showed some tremendously wild and wacky-looking ones from their data set. The measure of interest for probing the universe is this so-called scattering time, or the scattering width of the event. You can see here again the width of the emission varying as a function of frequency. That may be due to propagation of the radiation field through a turbulent medium with density inhomogeneities, which is to say by measuring the scattering, you can place constraints on the densities and its motions within the gas. I call this a signal, although it's an inference more than a signal, if the event is localized to, to a galaxy, and we have a methodology for doing that. We call it PATH. We've developed this Bayesian framework for identifying what's the most, probabilistically, what's the most likely galaxy to be hosting the event. This can be used for any transient phenomena, but we've been adopting it for fast radio bursts. And for subarc second localizations, typically the posterior probability for one galaxy approaches unity. This is one example. And in that case, the redshift one obtains with, say, an 8-meter class telescope provides you an inference or pretty direct estimation of the redshift of the fast radio burst. One can also observe the galaxy in multiple wavelengths, at a range of wavelengths, to assess its properties. I refer you to the talks that we've heard earlier this week in the symposium for some of the leading work in that area. Standard SED modeling and analysis of the multiband data provides estimates of the galaxy properties, stellar mass, star formation rate, star formation history, and the like. And so altogether, for individual FRBs, at least in principle, one can get a whole slew of signals and measurements that can then be used to probe the galaxy itself or the intervening material. And this is some example for one of the FRBs most near and dear to my heart. OK, that was a quick summary of the measurements that we can, at least in principle, obtain for individual FRBs. Now, how do we use them to probe the universe? Before getting into individual examples, I want to reemphasize something that Vicky touched upon, which is that a number of these measured quantities are integral quantities. That is, all of the material, in principle, between us and the event can contribute to the signal. That's especially true for the rotation measure and dispersion measure. It's also true to the scattering broadening, although in a somewhat different fashion. And so to cartoon that, the fast radio burst, which exists in the very distant universe and travels through gas and magnetic fields within its own host galaxy, those contribute to the signal. The cosmic web, all the material in intervening galaxies and the intervening intergalactic medium can and do contribute. Material in our own local group, our own galactic halo, and our own interstellar medium can and will contribute. I often refer to fast radio bursts as a blessing and a curse. The blessing is you're sensitive to all the material in the universe. That's got great scientific power. The curse is that you're sensitive to all the material in the universe. And so if you're interested in a particular component that is cartooned here, say the cosmic web, one of the things that's most near and dear to my heart, you have to contend with the other contributing factors to that signal. And we've developed and are developing techniques to do that, but it's certainly not trivial, and I want you to keep that in mind. And I will remind you as we go. OK, so I'm going to begin, as I said, by sharing a result related to our own measuring signals, probing the interstellar medium of the host galaxies of these FRBs. Here again, pictured as one host galaxy for an individual FRB, 2019 0608b, and its localization. The concept is we have a random, I put quotes around the word random. It's unlikely FRBs are coming randomly from within their hosts. That's an ongoing area of research. The offsets are pretty extensively distributed from in close to the center to out to the outskirts. But I guess calling it truly random would be a stretch. But nevertheless, a range of distributed impact parameters from the center of the galaxy. That's clear from the data. Of somewhat normal-looking galaxies. I'll show you a plot for context in a moment. And then a range of ways to probe the interstellar medium. The dispersion measure, in principle at least, can give us insights into the ionized gas within that galaxy. The scattering time can give insight into the density and turbulence within the interstellar medium. And the rotation measure, an inference on the magnetic field strengths of those galaxies. I won't, at least in the case of individual galaxies, talk about the dispersion measure. I'll come back to it at the very end. But that analysis is wrapped in with our understanding of the cosmic web. so the two are not easily separable. There's some excellent presentations on using the scattering times to infer properties of the galaxies. I refer you to those presentations. Will be one at the end of the day in room 101. Please come by for it. And I'm just going to focus in this presentation on the rotation measure and remind you that it's an integral quantity. Our own galaxy contributes to that. We have models for its value along different directions out of our galaxy. And there's evidence that there are local contributions, that is the very local environment to the FRB is likely contributing, and that makes this a little bit challenging, but nevertheless, let's proceed. So I'm presenting results from a paper in preparation, likely to be will be submitted by the end of the summer by Alexandra Mannings. And it's an analysis of the rotation measures from 9 FRBs that are securely associated, very securely associated with their host galaxies. Here's one of the 9. There's its galaxy in the localization pictured. On the right-hand side, we're showing the what is akin to a color magnitude diagram. Here it's stellar mass and star formation rate. The gray histogram in the background are normal galaxies from a large survey of the redshift around 0.3 universe, not too distant universe. The big solid band is what's called the primary set of the locus in the star-forming region is called the star-forming main sequence. The majority of FRB host galaxies lie close to it or even within it, but there are a handful of systems that are somewhat quiescent, not forming stars too aggressively today. And this is what I mean by a normal sampling of galaxies, a range of stellar masses, a range of star formation rates, following the main locus of traditionally observed galaxies. Each of those has a well-measured redshift. Here are the 9. Redshift on the x-axis. The y-axis is the absolute value of the rotation measure for the FRB, with the galactic contribution, or an estimate for the galactic contribution, subtracted. So these have been corrected for the Milky Way, which is a small correction typically. And you're to be impressed that there's no significant correlation with redshift between the rotation measure and redshift. That's not a surprise. We have not expected that the cosmic web would contribute substantially to the rotation measure. There is ongoing work, or there will be work to infer that. Talk to Brian Gensler if that topic excites you. But the inference we have from this small but still significant sample is that the RM cosmic contribution is small. Otherwise, we would have expected some potential trend with redshift. That means that the rotation measure we observe at RM FRB is dominated by the other 2 components, the Milky Way, which we have a model for, and the host. And so we can estimate the host contribution to the rotation measure simply by subtracting off the estimated Milky Way contribution. So I'll do that for the next few slides. If that inference is correct, that the rotation measure is dominated by the host, we may expect to see correlations with properties of the host, and we do. On the left is a scatter plot of that RM host quantity versus an estimated dispersion measure of the host. Happy to discuss in the question session how that's done. Here, positive correlation at really 99% confidence, 90% confidence. On the right-hand side, the rotation measure is a function of the offset of the event from the center of the galaxy, normalized in effective radius of the galaxy. And that's an anti-correlation, which, again, you might expect if you're probing outer regions of the ISM. You may expect the magnetic field to be weaker as well, or the rotation measure to be weaker as well. Small samples, small, weak correlations, but still, at least this stage, compelling that the RM that we're detecting is primarily due to the host galaxy. Last point for this set of the presentation is to put the 2 together, this estimate of the DM from the host galaxy and the rotation measure from the host galaxy. Approximately, crudely, the ratio of those 2 with some normalizing constants give you an approximate estimation of the magnetic fields within the galaxies. That's shown here as the series of lines. So 1 microgauss for the dashed line up to 10 microgauss for the dashed dot. For context, the Milky Way's kind of ambient magnetic field strengths, a few to several, maybe to 5 microgauss, with variations throughout the ISM. For this sample, with the exception of the one data point that lies way up there, the magnetic field strengths inferred for the ISMs of these normal galaxies is small, even smaller than what we typically measure in the Milky Way. It's only 9 galaxies. This is where we are today. Stay tuned for a sample of 100 or hundreds in the next year or two to follow. It's a very fruitful path forward for inferring aspects of the, in this case, magnetic fields of galaxies with a wide range of stellar masses, redshifts, and other properties. Transitioning to using FRBs to probe the outer halos, or the halos of galaxies, individual galaxies. I show here an example from Liam Connor and collaborators, a very exciting one. The galaxy pictured is M33, M31 must be around here somewhere. And this FRB that they detected, while not very precisely localized, is precisely enough localized to be clearly out in the halo, or intersecting the halo of M33. We saw the other day a handful of others that were detected in a similar fashion, also near M33 and M31. This is what I mean by probing coincidentally as the halos of individual galaxies. So FRBs in this case provide a random skewer through the halo of some completely unrelated foreground galaxy, or possibly more than one galaxy. This is a probe of the so-called circumgalactic medium. I'll call it CGM for short. And again, the signals that are present in the FRB allow us unique, in this case, estimations of the ionized gas profile, something we folks that also use quasar absorption lines have been trying to nail down for decades now. The scattering measure gives us some insight into electron densities of the gas out in that halo. Also a very difficult quantity to measure with any other technique. And the RM, as with the interstellar medium of the galaxy, we can get some inference on the magnetic field strengths out in the halos of galaxies. The challenges with this approach are you need this chance coincidence to occur. It's rare. Most sightlines will intersect a halo, but very few will intersect the inner parts of the halo where much more of the action will be taking place. But it's not negligible. It's not a negligible probability. I will focus on these two measures, the scattering, with the implications of the scattering width and the rotation measure for the halo gas of the individual galaxy. The host galaxy is a contamination here, and that is to say, again, these are integral quantities, or at least additive quantities in some respect. And so the conservative folks amongst you should be aware that constraints are really strict upper limits, and we'll treat them as such. Here's the example in question that I was most involved in. The red contours are the localization of the fast radio burst, which you can see land right upon a galaxy whose redshift's around redshift 0.5. Coincidentally, there's a second galaxy here at the center of the image at a foreground redshift, 0.367, that is sufficiently offset from the FRB itself that has nothing, it knows nothing about the FRB host galaxy. These are completely physically distinct. They're just a chance projection on the sky. And close enough in angular separation to imply that the FRB sightline penetrated the halo at about 20 kiloparsecs distance in projection. The galaxy in the foreground is pretty massive, a few times 10 to the 10 solar masses in stellar mass. The FRB signals for this individual event were weak in the sense that the scattering was non-detected. There's no evidence that the pulse had been broadened down to a limit of about 40 microseconds. And the rotation measure measured was also small, about 10 radians per meter squared. Individually, those place pretty much unparalleled constraints on the electron density and magnetic field within the halo of this galaxy. This figure describes that directly. The hatched regions are ruled out by the observations. So the upper limit on the scattering width sets a strong upper limit on the density of the gas in the halo, at least within the context that it has some motion, some turbulence within it. And then the diagonal hatch regions are a joint constraint on the product of the magnetic field and electron density in the halo. The yellow line was an inference for the magnetic field strengths in galactic halos from a previous study. It's clear, at least for this individual halo, it's completely inconsistent with those inferences. And then the band regions were some guesses, really indirect inferences on the electron density within halo gas. Certainly the more extreme models have been ruled out by, at least for this one galaxy. Last, let me go to the largest scales. So we're going to probe now the cosmic web in its most grandiose fashion. When I say cosmic web, I want to emphasize the fact that it's not what I would call the intergalactic medium alone. It includes everything, the galactic halos, here the orange blobs that you can see within this computer simulation of the cosmic web. So galaxy clusters, individual galaxies, small, even dwarf galaxies, galactic halos are embedded within this cosmic web, and they contribute to the signals that I'll be describing. And then the diffuse gas, the voids, the filaments that span between individual halos or groups of halos, that's what I do refer to as the intergalactic medium. And that, of course, also contains baryons in its own plasma that will contribute to the signal. So cosmic web is the combination of both these galactic halos and the intergalactic medium. What really got me excited about fast radio bursts was the opportunity to study baryons throughout the universe. And I was especially motivated by the following. What's shown here is when I give public talks, what I highlight as the most compelling evidence in my mind for the notion of Big Bang cosmology. What is plotted in the two, in the gray and in the blue, are separate measurements of the baryonic mass density, omega baryon, that's the x-axis, from two completely distinct experiments. The gray is the cosmic microwave background, so analysis of the acoustic oscillations imprinted in the CMB. Roughly speaking, the heights of the first peak in the acoustic oscillations to the second gives a constraint on omega baryon. And as you know, the CMB is measured primarily with our satellites at microwave wavelengths, and is a signal that came from about 300,000 years after the Big Bang. The blue swath is an inference of omega baryon from measurements of deuterium in quasar absorption lines, research that I've at least on occasion contributed to. It's the ratio, it comes directly from the ratio of deuterium to normal hydrogen or total hydrogen. So now here the observations are spectroscopy from optical telescopes at high dispersion. And the underlying theory is not CMB, the underlying theory is Big Bang nucleosynthesis. So completely different approach, completely different framework for the analysis, completely different data set. And the two agree to very high precision, sub% precision, to give the same omega bay h naught squared measurement. As I say, really a triumph of Big Bang nucleosynthesis. We've known about these measurements for a few decades now. The deuterium came first, the CMB shortly thereafter, in close agreement. And in 1998, Masataka Fukugita and collaborators pointed out the following conundrum. Those two measurements I showed you in the previous slide, I'll go back to it. Again, the CMB comes from the photons released at recombination, so about 300,000 years after the Big Bang, still early universe. The blue is from Big Bang nucleosynthesis theory, about 7 minutes after the Big Bang. Both are early universe measurements. Neither of these rely on data from the last 14 billion years of history. What Fukugita and collaborators did is look to confirm, or test at least, the measurements that were very new at the time on deuterium. And they did a census of baryons in the local universe. And this lovely Pac-Man in Pac-Man Plus diagram is the results of their work. They counted up the amount of baryons in stars, so survey galaxies, add up the mass of galaxies and how many there are in our local universe. That gives the orange and the cyan wedges. Use 21 centimeter observations of hydrogen gas to infer the atomic component, that's the red wedge. Use CO measurements or some other proxy for an estimate of the molecular gas, that's the gray wedge. And then use X-ray telescopes to directly estimate the amount of material in the hot plasma of galactic clusters. And what they emphasized at the time, and what held true for the subsequent studies, was that the majority of baryons were unaccounted for in this direct census in the local universe. And this beget what became known as the missing baryons problem on cosmic scales. Come on, slide. Technical department, did we freeze? There we go, thank you. The missing baryons problem, which is that of order half or more of all the baryons in our universe appear to be missing. Yeah, maybe has my device died? I can go back to maybe I don't know if the mouse will work. Theoretically, very shortly thereafter, after the publication of that missing baryons problem, the theorists went to their computers and said, okay, if we're missing half the baryons, where are they? They came up with a concept now known as the warm-hot intergalactic medium, or the WIM for short. So the hot gas in the filamentary web, cosmic web of the universe, is where the majority of these baryons are located. The phase diagram on the right describes the density and temperature of that gas in the computer simulations. It's low density diffuse gas. It's hot, warm hot, 1 million degrees, 10 million degrees. Very difficult to phase to measure with our telescopes. Nevertheless, it gave us a target, we observers, to go after, and many of us spent about 20 years and gobs of telescope time and observations to try and identify this elusive WIM, probably in excess of $50 million US dollars in operations alone, and we're really stymied. And that's where we stood when fast radio bursts really entered the scene. So back to the cosmic, how do fast radio bursts enter the picture? Quite directly, to be honest, and that's what's so beautiful about them. The cosmic contribution to the dispersion measure that Vicky introduced, here's the integral, it's also integral form of it. It's the integral of the free electrons in the universe, the average electron density. It's also subject to our cosmology, and the amount of baryons in the universe, so omega baryon, as provided here on the right-hand side. This is a direct prediction of cosmology. Given a cosmological framework, say your favorite Planck cosmology, WMAC cosmology, really doesn't matter. You get an estimate, direct estimate of how this DM contribution will vary with redshift. Thank you for the spare. Okay, thanks. Here's a plot of DM cosmic versus redshift, given the omega b measured from CMB and BBN, given our knowledge of this lambda CDM universe. That's what the prediction is directly from the model. There's also a predicted, the black line is what's directly predicted from cosmology. There's a model, one can introduce a model for the scatter in the cosmic web. That's what's shown here in the gray. So there's a physical intrinsic scatter to the mean relation, which is expected due to structure formation, can be predicted from simulations, and is now being tested by our data. This is where we stood prior to localizing a handful of events. And in 2020, JP McCord and collaborators produced this result, the first test of this model, the real first test of are the baryons, the so-called missing baryons, actually here in our universe, to be detected with fast radio bursts? The answer was a clear yes. And this led to our putting to rest, effectively, a couple decades worth of effort in trying to find or locate and detect the missing baryons. We now refer to this as the McCorrelation in honor of JP, who unfortunately passed shortly after this publication. Here's an updated version for 2022 from showing 16 fast radio bursts detected with the ASCAP telescope. I'm now plotting not just DM cosmic, but DM cosmic plus the host contribution, which I'll refer to as the extragalactic dispersion measure, or DMEG. The black line, therefore, is not just the prediction from cosmology, but includes a halo component. Here it's about 200 units per parsec inverse square inverse cubed centimeters. Nevertheless, you can see now with an enhanced sample, still a very good description. The model is still a very description of the data, and the correlation is holding up quite nicely. And again, the scatter about the line is physical and expected, and is primarily due to the variance in the host galaxies and in the cosmic web itself. Where we have proceeded now is to forward model these distributions to gain further insight into the universe. We're not satisfied with having detected missing baryons. We wish to use to push further on the cosmological implications. Here in the this colored figure, the colors indicate the probability, a forward model, a probabilistic model of the DMEG distribution for here the ASCAP telescope. And the black dots are measurements from the same telescope. Let me point out a few of the salient features of what you get when you forward model, and make predictions for the ZDM distribution. This cutoff at the upper right end of the figure are due to the energetics, the assumed model for the energetics of the FRB, and telescope sensitivity. As to say, with ASCAP, we don't expect to be detecting FRBs much beyond a redshift of 1. The long tail, the long vertical distribution to the PDF is due to tails, predicted tails in the cosmic contribution, and here modeled tails in the host contribution. And then this cliff, as we call it in the bottom of the PDF, is set by both the cosmic distribution and the Hubble's parameter. And so in a paper released this week by Clancy James, presented here by S. and Gosh, we've placed some first estimates on the Hubble's constant from that type of analysis. Here are the results. Here's the punchline, really. And not so precise estimation, but still a nice demonstration of some of the power one has on here H0, the cosmological parameter from the DM and Z measurements. They also provided a forecast for the precision one may achieve, at least within the context of this model, from a survey at 100 independent redshifts. And there you'd be achieving or pushing towards 5-ish% precision. Let me wrap up with 2 slides. I think it's just two or three slides. The future, as Vicky alluded to, is very bright for this field. I'm plotting in this figure in blue the number of published FRBs, at least as of a month or 2 ago, that I had my hands on. You can see the exponential rise in that curve due to the imprint of CHIME. Fantastic FRB producing machine. The red curve is the number of well-localized, say arc-second-ish FRBs. That too shows effectively an exponential rise. And this is prior to the fact that additional systems are just now turning on. There'll be additional exponential bumps as we head into the next few years. So where do I think this field will go in terms of probing the universe, using FRBs to probe the universe? I've kind of broken it down. This is purely my own personal opinions on where I think things where we might reach in the years to come. I think it's highly probable, if not certain, we will have wonderful new constraints on the turbulence of gas in the ISM of the host galaxies. We're getting that already to some extent. Cross-correlating the FRB signals with foreground galaxies will lead to inferences on the gas profiles of the circumgalactic medium, which in turn places unique constraints on galactic feedback. The diagram at the bottom is from the so-called flim-flam survey, which we heard about on day 1 of our conference. And there's many other efforts. There'll be other efforts underway for that. I feel optimistic. No, I think it's probable we can get to an estimate of Hubble's constant of 5%. That I'd be willing to stake a claim to. and that we'll be inferring wonderful new measurements of the halos of M31 in our own galaxy, especially with the CHIME experiment. I'm optimistic that lensing measurements will begin to play a role in using FRBs to probe the universe. Liam Connor gave us a wonderful talk on that at the start of the conference as well. Maybe we can push H0 to 3%. That's on the optimistic side. Maybe we'll be probing helium-2 ionization using FRBs that extend out to a redshift of 3. And hopefully we'll be setting new constraints on the IGM magnetic fields. And then on the maybe overly optimistic end, from my mind, whether we'll ever push into H1 reionization, so out into the redshift 5, 6, 7, 8, 10 universe, or place constraints that are especially meaningful dark energy, or H0 to 1%. That's probably pushing things, but it is nice to let those who have other toys to play with have something to work on as well. And with that, I'll end the presentation. Thank you.
Thank you very much. Let's open the floor to questions. Yes, please come to the microphone if you have a question. Also encourage those online as well. So
Thanks a lot for the really interesting review of cosmological implications. I had a question on the revised pie chart for the baryons now with the new results from FRB. So if I understand correctly, previously we had about a quarter which was called missing, and then there was another sort of quarter in Lyman alpha forest, kind of diffuse H1 systems. So now, is it the consensus that both of these are sort of similar phases, or is there more to it?
All right, I'll rephrase your. Yes, since after Fukagi's paper, there were additional estimates of just the diffuse and cold intergalactic medium, so what's traced by the Lyman, what we call the Lyman alpha forest. 25% is a fine number. It's pretty uncertain, but that's a good number to go with, which left about half for this warm, hot intergalactic medium. Today, we've detected those baryons, but not well localized them. So placing constraints on the WIM directly is one of the ongoing activities. It's something you can do by cross-correlating the signals with foreground galaxies. But that is the work that is really being done now and not something that we have an answer to.
Thank you.
While the next person's coming up, I'll just ask a quick question from online. Someone's asking very interesting results on RM host. The outlier with RM 10 to the 5 is reminiscent of repeaters like 121102. I'll just pause there.
It is R1.
Yes. Okay. That's what I thought. Okay. Thank you.
Hi. Thanks for the great presentation. I had a question about how you compute the RM host estimate. How do you compute, or how do you account for the foreground Milky Way and IGM contributions?
Right. So in that calculation, we've adopted a model by Opperman and colleagues who used AGN across the sky to build up a model for the galactic RM contribution. So that's a straightforward model. It's in the same spirit of NE 2001, if you know that, for the interstellar medium of dispersion measure contribution, but now for rotation measures. For the intergalactic medium here, I've just adopted the ansatz at zero contribution. It won't be zero exactly, but it's expected to be small. There's no evidence that it's contributing in the existing data.
All right. Thank you.
Yeah.
Sorry, while that person's approaching the microphone, another quick question from online. Thank you. One quick question is that, as in the case of the GRB community, is it true that a significant proportion of the FRBs have no detected host galaxy coincident with the burst location to deep limits either, or it's just an issue of poor localization? If so, what's the statistical properties of hostless FRBs in terms of DM and so on?
So of order 30 FRBs that I'm aware of to arc-second precision, 2-ish don't have a obvious galaxy at the location. Maybe 3. 10%. Let's call it 10%.
Okay, thank you. I think this will be the last question. Thank you very much.
So really cool work on the Faraday rotation measure. Do you have a sense for the theoretical convergence, whether analytic or from like fire simulations, on how much RM we expect from foreground galaxies, or do we observers have a blank slate?
So I think the question was, from numerical simulations, what are the predictions for the rotation measure in the halos of galaxies?
Yeah.
After the publication of the one I showed with the upper limit constraints from 2018-11-12A, if you know your FRBs. That was used to compare against, I don't remember whose flavor simulation, unfortunately. It might have been, no, I can't remember if it was Fire. And they used to say, hey, our model is consistent with this upper limit from FRBs. So there's no tension, at least in that model. In parallel, now in the interstellar medium level, and this is Freyke, Vanderhout, and Roediger, and I forget the name of their simulation. But, sorry? Thank you. They have made an attempt to not randomly, place FRBs within their galaxies that they've simulated. If you place them close to star-forming regions, this is important. I mean, maybe it's an obvious point. The dispersion measures are way larger, much larger than what are observed. So they then place them more according to the dispersion measures that are observed and inferred host. And if you do that, then the rotation measures are consistent with the observations. But if you were to place them in star-forming regions, maybe, again, not so surprising, the inferred rotation measures from their models would be much, much in excess of what's observed.
Thanks.
Yeah.
Okay, well, with that, and we're at the end of the time. So let me thank Professor Kaspi and Professor Prochaska again for their wonderful plenary lectures, and I hope that we have converted some of you to potentially wanting to come and work in this very exciting field. And you're very welcome to come and join us in room 101 for the last day of our symposium today. Thank you very much.